Hi, my name is Suyong. Jana and I will present the recent work of our team at MIT with the title of Participatory and Computational Design of Improved Cookstoves. We introduce a hybrid approach to combine computational simulation, physical experiment, and participatory design to the largely unsolved and persistent problems of household energy in low and middle-income countries. We'd like to start by pointing out the overlooked facts and challenges of household energy. Nearly 3 billion people in low and middle-income countries rely on inefficient burning of solid fuels, including firewood, coal, charcoal, dung, and crop residues, to meet most of their household energy needs. Such household combustion of solid fuels has a significant effect on global climate, with the emissions contributing 3% of total greenhouse gases and 25% of black carbon emissions, the second most powerful pollutant contributing to global warming behind carbon dioxide. Moreover, household cooking and heating also contribute to local air pollution, resulting in at least 4 million deaths per year, especially among women and children who are often exposed for a long time while cooking meals. Previous efforts to provide solutions to these families have fallen short of succeeding due to a one-size-fits-all approach, unaffordable and unsustainable subsidies. Therefore, to meet these needs, women predominantly rely on self-built or locally manufactured energy appliances. Laboratory testing of several common cooking solutions by the US EPA shows that local products generally underperform compared to higher performing and more expensive products. Despite this, local products continue to be the most widely used by low-income families. Since these products do not meet targets for health and climate benefits, they are not counted toward global targets like the Sustainable Development Goals, thus leaving the local manufacturers ineligible for recognition and a place in the global sustainable energy access establishment. We are motivated by those challenges and have questions. Given our capabilities to design and engineer technologies at MIT, can we work with the most successful energy product suppliers to engineer high-performance and safe products for their consumers, especially with the small-scale artisanal manufacturers? And can those improved products follow a scale and replication trend like the Kenyan ceramic jiku of the 1980s, which quickly spread across Africa? So last year, we started working on an approach to answer these questions, and we quickly understood that there is more to this challenge than applying state-of-the-art engineering methods like simulation and laboratory evaluation. To be successful, our team has also applied methods of participatory design to work together with community members and local manufacturers. This graphic shows our hybrid design method and approach to achieving impact in a demonstration case in Uganda. We combine simulation, laboratory, and participatory design to create reduced order models, which will be converted into accessible design tools to assist practitioners in producing high-performing and safer energy products. We decided to start with a demonstration case, the Maka stove made by our manufacturing partner, Appropriate Energy-Saving Technologies in Soroti, Uganda. The Maka stove is a fairly standard Jiku-style cookstove and handmade by Ugandan artisans. While Maka offers many improvements over traditional wood fires to its users at an affordable price, our initial testing has shown that there is still room to improve their performance and safety. And since the stove makers are a tight-knit community in Uganda, the improvements that we co-design with AEST have a high chance of being taken up by other manufacturers if they are effective and suitable for the users. In this sense, understanding how performance is sensitive to specific design changes is important. However, repeating laboratory experiments with different designs is time-consuming and expensive, So we picked up computational fluid dynamics. We newly developed a shift model to simulate the Maca stove filled with charcoal, and by using the conservation laws, the detailed flow field, and the global parameters such as thermal efficiency, carbon monoxide, and soot emissions can be evaluated. Thermal power and emissions are highly sensitive to chemical kinetics. Solid fuels are converted to the final product through two main steps, which are pyrolysis from solid fuels to gaseous fuels and gas combustion. By adding chemical kinetics and emission models to the conservation laws, a model can predict heat, carbon monoxide, and soot generation. Based on this baseline of Maca stove, we plan to do the parametric studies to figure out how performance and emissions are sensitive to geometries and field conditions. Then such shifted result with participatory design will be combined in a reduced order modeling. Our partners at the lab use their own lab experimental facility to collect data to tune and validate shift simulation. In the BOM lab, we collect real-time measurement of emissions, burn rate, flow, and temperature profiles throughout a Maca stove use cycle.
This project would have likely followed the same path as many other household energy projects if not for the participation of the community members and organizations like AEST. They allowed us to take a hybrid approach that includes the involvement of Cookstove users in Uganda to closely inform design decisions. Despite restrictions during the pandemic, our team has been able to gather information from these participants to link user needs and preferences to features and metrics for Cookstove performance. We have identified the list of Cookstove features that can be optimized through computational modeling, such as the insulation layer and clay liner. These features can be optimized by modifying the dimensions or materials to improve the Cookstove performance. Our goal is to involve Cookstove users and manufacturers to understand their preferences and drive the design decisions in optimizing these features. The Cookstove features will be optimized to meet a set of performance metrics. A list of the desired performance metrics was generated through an understanding of the important factors to the computational model, as well as common metrics found in the Cookstove industry. The values for these specifications will be determined by a thorough understanding of the user preferences as well as acceptable standards. For instance, the metric of the time to reach water boil temperature is determined by knowing what Cookstove users find as an acceptable cooking time. To appropriately define the performance metrics, it's important to thoroughly understand the user needs. Through discussions with Cookstove users, manufacturers, experts, and prior literature, we generated a list of 12 comprehensive user needs. These discussions determined that the cookstove must be fuel efficient, cooks quickly, reduces smoke emissions, is safe, durable, affordable, serviceable, easy to clean, portable, easy to use, compatible with different fuels, and has an appealing appearance. To successfully design a cookstove that is desired by the users, the cookstove must fulfill all of these needs. To further understand these user needs and which of the needs the users find most important, a survey was developed. The survey includes several different question formats to best understand the user preferences and purchasing behaviors. For instance, rather than asking users which needs they believe to be most important, a conjoint analysis is used. A sample is shown here on the right. In this question, several hypothetical cookstoves with different specifications are presented to survey respondents, who are then asked to choose which they would purchase. This would allow us to understand how the different specifications rate in relation to each other. The survey was created with help of community partners to ensure its cultural appropriateness. It is currently being piloted with Cookstove users in eastern Uganda. Paper surveys will then be administered to Cookstove users with the help of community partners. Our hybrid approach involves linking the participatory design aspects with computation through a comprehension of the user needs, performance metrics, and product features. A thorough understanding of the user needs will be used to define the specifications for the performance metrics. These specifications will be used in the Cookstove model to optimize the product features. Linking these different components will allow us to design a cookstove that is optimized from an engineering perspective and guided by user preferences. Our next steps include completing the CFD model and validation testing, as well as the distribution of the survey to Cookstove users. In the future, we aim to modify this hybrid methodology so that it can be applied to other contexts as well, such that products in other regions can be driven both by engineering and user-focused design.